very brief background on what thermomechanical fatigue is and how we deal with it. And primarily, we're going to talk about how we deal with it how we deal with it in ANSYS ENCODE design life. The thermomechanical fatigue encompasses a group of failure mechanisms that can include the combined effect of fluctuating stresses and high temperature. Combined thermal stress cycles produce thermomechanical fatigue damage for a number of reasons. First of all, the thermal expansion and contraction induced stress, classic thermally induced stresses. Material strength decreases with increasing temperature. You can see the stress strain curves on the right. You can see as the temperatures increase, the tensile stress decreases. Material resistance to fatigue damage decreases with increasing temperature. You can see at the SN curves on the right with different temperatures, and fatigue resistance decreases as the temperature increases. Materials creep at high temperatures. These creeping voids accelerate fatigue cracking, and oxidation accelerates because of the voids and because of the cracking. So all four of these mechanisms can cause fatigue damage when thermal stress, high temperatures are combined with stress. TMF is an important failure mechanism for many industrial components, things like exhaust manifolds, exhaust mufflers, gas turbines, turbine chargers, etc. All structures that experience high stress or relatively high stress and high temperature. ANSYS ENCODE design life can evaluate four basic TMF approaches. First is the multi-temperature method. The second is Chaubosh method. The third is Chaubosh transient method. The fourth is the creep rupture. The creep rupture, it's actually six approaches. There's three basic approaches: multi-temperature, Chaubosh transient, and creep rupture can be added to any of those. So more traditionally, it's just added to the Chaubosh transient method, which is why we say four methods: multi-temperature, Chaubosh transient, Chaubosh transient plus creep. But creep could be added to the other two methods as well. The multi-temperature method is the simple, most straightforward method. It just uses temperature-dependent fatigue curves to predict fatigue damage associated with applied stress at elevated temperature. As you see, these are classic SN curves at different temperatures. Okay. This approach is applicable to moderate and constant, or at least slowly varying temperatures, particularly when the cyclic stresses are dominated by mechanical stresses. So you have a component that's seeing, moderate stress, moderate temperatures, maybe some thermally induced stresses, but they're not changing rapidly, and mechanical stresses that are primarily caused by pressure or loading. This method is applicable and will work fine. The next step up in complexity and application is the Chaubosh method. It's similar to the multi-temperature method, but it uses temperature-dependent Chaubosh fatigue curves to predict the fatigue damage associated with applied temperature, elevated temperature, applied stress, elevated temperature. And you see on the lower left, these are your temperature-dependent SN curves that are used in the multi-temperature method. To the right are Chaubosh fatigue curves. Okay? They're essentially modified SN curves developed using a nonlinear damage evolution rule. They include a mean stress correction and adjustments near tensile failure and endurance limits. So at very low stress near tensile failure, these curves tend to bend over more than the SN curve, and up at high temperature, high cycle, low stress range, the high cycle fatigue range, these stress tend to flatten out more, have more of a distinct endurance limit than the traditional SN curves. Okay. Other than that, you can see where they came from. This is the equation used to calculate them, and you can see there's a mean stress correction built into them. Okay. These are applicable to moderate or high temperatures. Again, basically applicable to constant temperatures or slowly varying temperatures. So these are more applicable. They're applicable to the same basic type applications the multi-temperature method would be, but they're more accurate at higher temperatures. The third method is the Chaubosh transient method. It uses a single master Chaubosh fatigue curve to predict the fatigue damage associated with the applied stress elevated temperature. The multi-temperature Chaubosh curves are classed onto one master fatigue curve using a normalization parameter, which is usually proportional to all the mechanical stress. Against on the left are the Chaubosh fatigue curves, the group of Chaubosh fatigue curves. They're classed into one curve, and the data points are failure points at different temperatures. So these are collapsed down to one universal fatigue curve. The normalization pattern is then used to adjust the actual stress to calculate an effective stress for comparison to the Shabbat-Master fatigue curve. It converts the FE stresses to temperature normalized stresses. In the middle here, you can see this is the temperature profile changing. This solid line is the calculated stress on the FEA, and this dotted line is the adjusted normalized stress using the Shabbat normalization parameter. This method is applicable to moderate and high temperature and varying temperatures and firmly induced cyclic stresses. So you have a component that sees high temperatures where the temperatures are varying, maybe varying rapidly, and much of the stress is caused by the firmly induced stresses. The multi-temperature nor the Shabbat method would be applicable, but this Shabbat transient method will work. Okay. Creep rupture can be added to fatigue damage from either multi-temperature Shabbat or Shabbat transient methods. We generally think of it as being to contain a complete creep fatigue solution. We tend to think of it being added in the Shabbat transient method, but the method stops matters. The other method is applicable at very high temperatures. Creep damage is thought to be significant if the temperature exceeds 1/2 the melting point in Kelvin. The image is an image from the advanced glyph of design lake. You can see there's only three creep models that accepts Larson-Miller curve, Larson-Miller polynomial, and suppose it doesn't have the full range of creep capability that mechanical has. Now, this is a real brief table, real small table to show you what based upon your temperatures and stresses, what type of method might be most applicable. Let's look at the least severe case, which are mechanically induced stresses with a moderate temperature. For this method, you would calculate the stress using a linear FEA. You would calculate the fatigue damage using any of the methods, SN multi-temperature, EN multi-temperature, or Shabbat. You don't need rupture creep in this case because it's a moderate temperature. Let's look at the most severe case, which is high temperature and firmly induced stresses. In this case, you probably want to calculate your stresses using elasto-viscoplastic FEA. You would calculate damage using a Shabbat transient plus creep. And the other two are subsets of that. For mechanically induced stresses with a high temperature, you probably calculate your stresses using linear or elastic plastic FEA. You would probably calculate the damage using a Shabbat as opposed to Shabbat transient method plus creep. And for thermally induced stresses but only moderate temperature, again, you'd probably calculate your stresses using linear or elastic plastic FEA. And you calculate your damage using the Shabbat transient method. And because it's moderate temperature, creep's not an issue. We have some resources for thermomechanical fatigue if you're interested in learning more about it or practicing with it. There's at least 3 work TMS samples in the Design Life Health System. The one that's probably most complete is work example number 12, thermomechanical fatigue. Pretty thorough example. We walk through a couple of different methods. We also a very good presentation by Dr. Andrew Halfpenny, Chief Technologist, HPMN code. It's a couple years old now, 2012, but the basics of thermomechanical fatigue obviously haven't changed, and all these methods may have been refined a bit or some more capability data, but it's still basically the same. You can access this off their website. You can download the recording and listen to it. It's a very good presentation. I would recommend anyone who doesn't know a lot about thermomechanical fatigue but interested in learning it. It's probably better just to listen to Dr. Andrew Halfpenny explain it than you to try to read it in a textbook. So in summary, thermomechanical fatigue is a critically important failure mechanism for many components. Design Life has 4 basic approaches: moderate temperature curve method, the Shabbat method, Shabbat transient method, and the creep rupture. And creep rupture can be modeled with fatigue damage methods. Any of those 3 fatigue damage methods to model a complete fatigue plus creep damage. Okay, searching for solution, obviously a rehash, customer portal, type in your keyword into the solution in the search window, hit search, and in this case, if we type in thermal fatigue, one of the first knowledge materials that we'll come up with is this knowledge material 458296. It's a frequently asked question, and it is does the ANSYS fatigue module in the ANSYS fatigue module is it possible to specify SN curves for different temperatures? Basically, is it possible to do the multi-temperature method using the anti-fatigue module rather than design life. This question I expect to come up more and more frequently now that we provide the fatigue module free of charge with the enterprise license and above. So more people are using the fatigue module, so we're getting more questions about. I expect this question will pop up now and then. The answer is no. It's not possible to adjust the SN curve for temperatures. We can't specify temperature-dependent SN curves in engineering data. So, you can take a couple different approaches. The most common approaches taken by users are to manually pre-adjust one SN curve using the highest temperature in the model, or use multiple SN curves based on different temperatures. What I mean by that is you could create different materials. Each material could only have one SN curve, but you could create, let's say you had structural steel. You could create structural steel 1, structural steel 2, structural steel 3. When structural steel 1 might be an SN curve at 70 degrees F. Structural steel 2 might have an SN curve at 300 degrees F. And structural steel might have a SN curve at 600 degrees F. Okay? And then you could assign the material property inside mechanical based upon the maximum temperature. You have to do it the two-part approach, obviously. You run your thermal analysis, find out which areas have the highest stress. You assign material based, the material based upon the temperature-dependent fatigue curve you want to use for that material. Then you could do a fatigue calculation, basically the whole model, even though it's one material, you're using 3 different SN curves based upon the temperature in that model. Okay? The first method just says, you pick the worst case temperature throughout the whole model and use that SN curve. First method is always simplest, but it's probably very conservative. The second method can be a little bit less conservative. Obviously, the number of materials you pick, the number of SN curves, and how fine you resolve your model is up to you. You have 1, 2 materials, 3 materials, 10 materials, whatever you want. The second solution that will pop up is solution or knowledge material 2034922. Again, it's a frequently asked question. This is a more specific question about what design life does behind the scenes. And this came up in an SR one time. Individual asked this question. And basically, how does the temperature load provider in ENCO design life associate temperature with the cycle? What I didn't explain here, but how you handle temperature-dependent fatigue inside design life is you use what we call a hybrid load provider. And one load provider for temperature, one load provider for stress. And the temperature load provider maps temperature over time and associates that temperature with whatever stress you're using in your stress combination, so you know what stress, what temperature goes to what stress. The question is how to do that. Okay. For stress-like fatigue, the temperature is evaluated for the individual cycle. So in each cycle range that you're looking for, each bin in the range flow counting, there's going to be a certain temperature associated with that with each cycle. Okay. For strain-like fatigue, the maximum or average temperature is chosen for the entire temperature history. Strain-like fatigue does not allow cycle-by-cycle temperature assignment. There's elastic properties of changing the temperature. This change does not allow the hysteresis of the flows and stress strain tracking rain flow procedure. So in this case, stress life is probably more accurate in how they apply temperature. But there's other reasons why you may or may not want to use strain life in the analysis as well. This is an indicator how design life handling the temperature behind the scenes. And the third one is the last one, and you'll see the frequently asked questions pop up on the knowledge-based search because I just created this knowledge material a few days ago, so it's not in the system yet, in case I haven't checked it yet. But again, I'm fairly certain you'll get to it by searching for thermal fatigue, and the number associated with this is 2048632. So if anyone wants to look at it now, they can just search for that solution number, it'll pop up. The question is, there a presentation explaining the thermal mechanical TMF capabilities available in the ENCO design life? And the answer is yes. I attached a presentation from the 2015 Multi-Physics Summit explaining TMF capabilities available in ENCO design life. And if you click on that attachment, you'll get a link to this PDF. It's similar to what I presented today with a lot more detail behind the scenes about how you do it in design life, which splits you use, and how you specify it. A fairly detailed approach of how you use design life to thermal mechanical fatigue. I think with that presentation, along with the work examples inside design life health system and the presentation that you can listen to from Dr. Andrew Halfpenny, will give you a pretty good background of understanding the basics of thermomechanical fatigue in design life.